Hey gang! So in today's thermodynamics video, we're going to talk about why physical properties are important, reading a phase diagram, and then defining terms related to a phase diagram. Now, in the previous thermodynamics lecture 1 video, we talked about why thermodynamics is important. We talked about that thermodynamics is related to energy generation, whether that's at a power plant using steam turbines or using wind turbines. We've talked about that it's also used in the transportation industry with your planes, trains, and automobiles. And thermodynamics is used when you're dealing with chemical separations and getting pure chemicals. Thermodynamics governs what's physically possible and impossible. So there's a lot of reasons why we need to study thermodynamics. And one subtle item to get us all started and is also really important in the world of thermodynamics are our physical properties. And you may be wondering, why are physical properties important? Well, let's look at a power plant where we're using steam to generate energy. In this process, you have a boiler that's generating steam. You run the steam through your steam turbine. And after it goes through the turbine, we've generated energy. We then go to a condenser. We'll condense our steam into water. And then we run that water through a pump, sending it all back to the boiler to make more steam. Now, as you're doing this whole process, what's going to happen is you have a question of, well, how much energy do I need to generate, to make my steam? How much energy am I, releasing as I condense my steam? And how much energy is going into and out of my system when I'm generating energy and I'm pumping my water? So there's a lot of unknown factors when in this whole process, even though it seems really simple. And the reason why this is there's unknowns is because the physical properties. What are what state am I in? What's the temperature and pressure? That all governs the energy inputs you need as well as what energy you'll get out of your system. And that's where the phase diagram comes in because it shows this interrelationship between your phase as well as temperature and pressure. And then that later leads into when we do energy calculations, how much energy we'll get out, as well as how much energy we need to put into different situations. So with our phase diagram, right, on the y-axis, we're going to have pressure. On the x-axis, we have temperature. Now, if you pick a point on the y-axis and you just go all the way across horizontally, what you're going to do is you're just holding pressure constant. It's isobaric. We're just changing temperature. Similarly, if we navigate along the moving upwards, we pick a point on the x-axis and we just go upwards vertically. We are now just changing pressure while holding temperature constant and we're isothermal. So now that we know how to navigate our diagram, we're going to now show something representative. And on this diagram, we've got different phases at different temperatures and pressures. And we'll start off with, if we have a high pressure, we got a low temperature, you guessed it, we have a solid. Now with our solid, if we hold pressure constant and we just decide to change temperature or increasing temperature, eventually we're going to melt that solid and we're going to make a liquid. And as you go from solid to liquid, there's a transition zone or transition boundary. And that's called your melting point or freezing point. That's the temperature at which your solid liquid transition occurs at a particular pressure. Now, after you made your liquid, now let's pretend that we're going to hold temperature constant and we just decide to lower our pressure. Eventually, as you lower your pressure enough, what's going to happen is you'll make a vapor. And you guessed it, we've now crossed another bound. We've transitioned from liquid to vapor. And that point, that boundary between liquid and vapor is called your boiling point. Or sometimes, less often, it's called your condensing point. And that's the temperature at which the liquid vapor transition occurs at a particular pressure. Now, the other thing to be aware of, and another term to know, is vapor pressure. So that's the pressure at which your liquid vapor transition occurs, or if you're dealing with a solid vapor transition, so you're at that line that's to the left of your liquid vapor line, that's where your solid vapor transition occurs. Now, within your diagram, there's a couple of also special points that you should be aware of. And the first one is this point where your three lines intersect, where now you have solid, liquid, and vapor all coexisting. That's called your triple point. And the triple point is the temperature and pressure at which your solid, liquid, and vapor states all exist in equilibrium. Now, as you probably guessed, there's only one triple point for each material you have. Now, if you decide to go along your liquid vapor line and you go to the ends of the liquid vapor line, there's another special point we hit, and that is called our critical point. And the critical point has obviously some corresponding temperatures and pressures, where at that temperature, that is called our critical temperature. Now, the critical temperature is the temperature at which no liquid phase occurs regardless of pressure. So we are so high in temperature, we can never form liquid. The other special feature of the critical temperature is that if you have a vapor and you increase your temperature, holding pressure constant, and you cross that boundary between the temperature below critical temperature and you go above that critical temperature, what now happens is that there's no phase change with your vapor, but there's a new term for your vapor. This is where we have a gas. And so what we normally use interchangeably as vapor and gas, there's actually a subtle difference between the two, where your vapors mean that you are below your critical temperature, while your gases are at and above the critical temperature. Vapors mean that you can go from a vapor to a liquid. Gases mean that you are at such a temperature you cannot form liquid. So now you know that there's clearly a difference between the two. Now, we just talked about critical temperature, but there's also, you guessed it, critical pressure. And so critical pressure is the pressure at which no vapor phase occurs, regardless of pressure. And now that we know, okay, so at the critical point, we have critical temperature, we've got critical pressure. The next question we probably have is, well, what happens if I go, above both critical temperature and pressure? What next? What do we have? And that's a great question, because that means you have a supercritical fluid. And a supercritical fluid is something that exists above both the critical temperature and pressure, but it also has properties that are between a liquid and a gas. And supercritical fluids, one of the applications of them is used as an alternative to liquid solvents. So it's pretty good at extracting different compounds from a raw material. And one example of that is using supercritical carbon dioxide to extract caffeine from coffee beans. And I know exactly what you're thinking, like, whoever would want to decaffeinate coffee? Well, I would. I very much appreciate it. But that's a topic for another day. But anyway, yeah, supercritical fluids are really important or have certain applications in industry. So now that you're seeing this interconnectedness between your phase, your temperature, and pressure, and you can read the stuff off the phase diagram, you see there's different places for all these phases to exist. There's different criteria to achieve each of these different phases. And there's terminology that's really important for the phases as well as when you transition from one phase to another. And so that's everything for today, since we talked about why physical properties are important and your phase diagrams. So thanks a lot for tuning in, and stay tuned for the next one.